Now let us discuss another good numerical problem from engineering mechanics by Professor Timoshenko, D.H. Young, Sukumar, Pati and Rao, Tata McGraw-Hill publication, 5th edition. This is again from the friction, problem set 2.7, solution to 2.110. So as you can well see in the diagram, there are two blocks. Referring to this figure, the coefficient of frictions are as follows. Mu1 is 0.25 at the floor, means here mu1 is 0.25, 0.3 at the wall here, that is mu2 is 0.3, and 0.2 between the blocks, between these two blocks, the friction here is mu3 is equal to 0.2. Now, the weight of this block is 4450 Newton and the weight of this one is 2225 Newton. Now, find the minimum value of the horizontal force P. This is the horizontal force that we are applying to the lower block that will hold the system in equilibrium. So, what is given, W1 is 4450 Newton, W2 2225 Newton, coefficient of friction here is mu1, here is mu2, and between the blocks is mu3, and the values are given. Now let us understand the problem. This block will try to move down due to its own weight. So this block will be pushed towards the left. So between the two blocks, this is the surface in contact. So there will be a force of friction which will be common to this block as well to this block. But we have to identify their directions. Now the upper block tends to fall due to its weight W2, that is 2225 Newton. So the lower block, this one, will be pushed towards the left. So to hold it in equilibrium, the system in equilibrium, we have to apply a horizontal force P to this side. And we have to find out the value of P. So P is the applied force to the left, from left to right on the lower block. So I have redrawn the diagram here showing the different forces. So now let me explain the forces and the angles, then it becomes simpler. Let us begin with the lower block, pull towards the right with a force P. The weight is acting vertically downward, means on the surface it will apply some action force. The reaction force is R1 on this block, and between this block and the floor, the coefficient of friction is given as 0.25. And since the upper block is falling down due to its own weight, this block, the lower block, will be pushed towards the left. So to oppose its motion, the force of friction F1 is to this side. And how much will be F1? Mu times the normal reaction. So this will be mu1 times the normal reaction here. Now again, let us look at this block. Since this block is trying to fall down due to its own weight W2, so the force of friction here between the wall and this block will be F2, will be to this side. And how much will be that? Will be mu2 times the normal reaction, that is R2. Action, this is the normal reaction R2. And again, since this block is trying to slide down, the force of friction between this block and this block here, for this block, the force of friction F3 will be to this side, and the same force of friction F3 for this block will be to this side. And how much will be that? That will be mu3 times the normal reaction, that is R3. Now, which is the normal reaction? R3. This R3 for this block and this R3 for this block at this point of contact. Now it is given in the original diagram, this angle is 60. Since this is vertical, this is 90. So we are left with 30 here. So this will be vertically opposite to this, so this will be 30. Since this reaction, action-reaction pair is normal to this surface, so normal means making 90 degrees, so we are left with 60 degree here, and the vertically opposite of this will be 60. So that's all. Now we can proceed. Now if you look at the upper block, this block, it is subjected to 5 different forces. What are those forces? W2, 225 Newton downward. Here, the force of friction, F2 mu 2 times the normal reaction R2, acting upward. F3 between the two blocks for this block is to this side is equal to mu 3 R3 is another force of friction. Now then then R2 is the normal reaction from here, from the wall. And then R3, another normal reaction that is between the blocks. So these are the 5 different forces acting on the upper block. So we have to draw the free body diagram. So now let me explain a little further. W2 on the upper block is acting vertically downward, so it doesn't have a horizontal component. R2 is horizontal, so R2 doesn't have a vertical component. F2 is also vertical, therefore this F2 does not have a horizontal component. So we are left with R3 and F3. So we are left with R3 and F3. None of them, neither this nor this. They are either horizontal or vertical. They make some angle. Therefore, F3 and R3 can be resolved into rectangular components. F3 makes angle 30 degree with a y-axis. I have redrawn here. R3 makes 60 degree with a y-axis. You can watch it in the original diagram and the diagram redrawn. R3 makes 60 degree with y-axis. F3 makes 30 degree with y-axis. So that is what I have explained here. So then the free body diagram. Now at this point of contact, at point of contact, you can, if you draw a horizontal line like this and a vertical line like this, so the horizontal line is your x-axis, the vertical line is your y-axis. So the forces are shown. The red lines indicate the force of friction, F2, F3, 30, 60, W2, R3, R2. So how I have shifted to one point? By using the parallelogram, by the vector method. Means given a vector, you can shift it parallel to itself. R2 is shifted parallel like this, then like this. So this is your R2. And W2 similarly, W2 is shifted parallel to itself and shown it here. Now R3 is shifted parallel and shown from the origin. Similarly F3 is shifted parallel to it and shown from the origin. And F2 also shifted parallel to it and shown here from the origin. Now let us apply sigma x is equal to 0. Now everything is self-explanatory. Sigma x, now x is equal to 0. Now the component of R3 means this one will be R3 times sine 60, and that will be opposed by R2, and the component of F3. The component of F3, if you drop a perpendicular from here to here, will be F3 times sine 30. So this is what we get by applying sigma x is equal to 0, means sum of the forces along x-axis 0 for condition of equilibrium. Now R3 sine 60, R2, and force of friction F3 is equal to mu 3 times R3 sine 30. Now what we will do here, we will keep R2 on one side, we will take these two other side to take R3 common. Now let us apply sigma y is equal to 0. Sigma y is equal to 0. F2 is along positive y-axis. The component of R3, that is this one, will be R3 cos R3 cos 60, not 30, R3 cos 60. And the component of F3, this one, from here to here, will be F3 times cos 30, R3 times cos 60. They are in the same direction, same as F2, and that is being opposed by W2. So is equal to W2. Now, so force of friction F2 is mu times the normal reaction, mu 2 R2. Force of friction F3, mu times the normal reaction, mu 3 R3 cos 30. R3 cos 60 is equal to W2. Now from equation 1, that is this equation, if you keep R2 on one side, take this to this side and take R3 common, we are in the bracket, we are left with sine 60 minus root 3 times sine 30. So put the value of sine 60, put the value of mu 2, put the value of sine 30, and this comes out to be 0.766 times R3. So your R2 is found out. Your R2 is found out. Now put this value of R2, in equation 2 here. Put this value of R2 here. Mu 2 is known, mu 3 is known, cos 30 is known, cos 30 is known, and since R2 is found out in terms of R3, if you put it here, then this equation will have only one variable, that is R3. So it can be solved. So let us put the value of R2 here in equation 2. So by doing so, the equation 2 reduces to mu 2 times R2 plus mu 3 R3 times root 3 by 2 plus R3 times 1 by 2. I have put the values of cos 30 and cos 60. It's not 30, this is 60. Cos 60. So now take R3 common. There are three terms. One term, the second term, the third term. R3 is common. So this is what we are left with in the bracket. So bring this to the right hand side. Your R3 comes out to be 2463.994 Newton. That is nearly equal to 2464 Newton. So R3 is found out. Now let us look at the lower block. Let me show you in the original figure. Then the redrawn figure. The lower block is acted upon by 6 different forces. 1, 2, 3, 4, 5, and a force of friction F3. 6 different forces. So if you look at the lower block, it is acted upon by 6 different forces. W1, R1, F1, mu1 times R1, the applied force P, R3, the reaction force between the blocks, a force of friction F3, mu 3 times the normal reaction. So I have not drawn the diagram again. Now this is horizontal, doesn't have a vertical component. This reaction R1 is vertical, does not have a horizontal component. This P is horizontal, does not have a vertical component. And here this R3 we have to split it, and this F3 we have to split it. So we are only left with two forces to be split into horizontal and vertical components. So we have to resolve only two of these, that is F3 and R3. So the free body diagram is drawn. Let us apply sigma y is equal to 0. The angles are already explained, how this is 60 and this is 30. They are explained. Just have a look once more. R3 makes 60 degree with vertical, and F3 makes 30 degree with the vertical. F3 makes 30 degree with vertical, R3 makes 60 degree with the vertical. And this is your force of friction F1. And this is the applied force P. So we have to only split R3 and F3. So if you apply sigma y is equal to 0, that is the sum of the forces along y-axis 0, R1 is along positive y-axis. Now if you drop a perpendicular here from this point to this point, will be R3 times cos 60 along negative y-axis. W1 is also along negative y-axis. Then the component of F3, if you drop a perpendicular from this point to this point, will be F3 times cos 30, that is also along negative y-axis. So R1 is balanced by these three forces. So R3 cos 60, W1 is known, F3 mu3 times the normal reaction cos 30. So if you put the value of R3, which you just calculated, then R1 comes out to be 6108.77 Newton. Right. Now then apply sigma x is equal to 0. Sigma x is equal to 0. F1 and the applied force P, they are in the same direction. And a component of F3, that is if you drop a perpendicular from the tip of this vector here, this length will be component of F3, that will be F3 times sine 30. So F3 times sine 30, P and F1, they are along positive x-axis, and that is being opposed by the component of R3 to this side, that is equal to R3 times sine 60. So P plus F1 plus F3 times sine 30 is equal to R3 times sine 60. Force of friction F1, mu1 times normal reaction there. Force of friction F3, mu3 times the normal reaction there, sine 30 is equal to R3 times sine 60. Now take these two terms to the right hand side, they will be subtracted, and now put the values. Put the value R3 which we calculated, mu1 is known, R1 is calculated, mu3 is known, to get P is equal to 360.294 Newton. So that's all about. Thank you for watching. If you find the contents are beautiful and is really helping you, feel free to pass on your comments. And if you have not subscribed, you could well do so. And thank you.